Okay, let's look at this example. A small quantity of liquid bromine, so it is a liquid, was dissolved in water in a glass volumetric flask and placed in direct sunlight in order to study the photochemical decay of aqueous bromine in bright sunlight. The concentration of bromine with respect to time is tabulated in the following table. So what you have is a raw data, concentration with respect to time, concentration of bromine. For the given data, evaluate the value of negative dc over dt for each data point by using graphical differentiation. So you are going to prepare a histogram. Okay, if you look at here, it is a decay of aqueous bromine. So you may have E and then B. Right? Then you may, because there is only one reactant, that is bromine, so most probably it is the decomposition of bromine. So you may start with negative Re equal to KCa alpha, the equation from the rate law equation, and another one is from mole balance, negative Re equal dCa over dt for the batch reactor. Okay, combine this one. Combine, you get this. For which negative dCa over dt is equal to KCa power alpha. Introduce natural log both sides, then you may find it that alpha is equal to the slope and k is the intercept. However, you need to determine first what is negative dc over dt by using graphical differentiation. Okay, I want you to solve this example. Do it in pair and one of you will submit it at Google Classroom. Make sure you write down your name on the paper. Okay, move on to numerical method, which is simple compared to the graphical methods. This method can be used when the data points in the independent variable are equally spaced. So it must equally spaced. From 0, T1, T2, let's say 2, 4, 6, 8, 10. It is equally spaced. What happens if it is not equally spaced? Meaning that you need to again plot the graph. Because it's not equally spaced, right? This is your T and this is your concentration. Let's say what you have is as the concentration, as the times increase, as the reaction time increase, obviously your Ca will decrease. So example like this. So by having this graph, you can identify what is the concentration at any time that you want. Okay, because this is there are here 5 points. It could be like this, as long as there are 5. So you are going to identify the value for equally spaced concentration with respect to time. So having the equally spaced data, dCa over dt can be calculated by the initial points given by this equation. Okay, what is your Ca naught? So 3 multiplied by Ca naught plus 4, Ca1 minus Ca2 divided by 2 delta T. So your delta T here is T1 minus T0 or T2 minus T1. They are equally spaced. It should be similar for delta T. That is for your initial point. Okay, interior points, meaning between initial points and last points, you are going to use this formula. So just be careful. For example, this is CAI plus 1. Meaning, for example, you want to have at T, this is T0, this is T1. Okay, at T1, So 1 plus 1 is equal to 2. So the formula will be 1 over 2 delta T. C, 1 plus 1 is 2. C2 or CA2 minus 1 minus 1 is equal to 0. CA0. Okay, so you just follow this equation. So this is numerical method. You can get this from the numerical textbook. Okay, and the last one is the last points whereby you are going to use this formula. Alright. So meaning that you may determine your negative CA over dt. dCA over dt. So this is example from fogler. Right. If you look at this example, you have two reactants. Okay, there are two reactants. Okay, you are given the reaction of triphenyl methyl chloride, triethyl, is represented by capital A, species A, and methanol, species B. Okay, most of the time, once you have given the chemical reaction equation, represent it in terms of A, B, C, or D. It was carried out in a solution of benzene and pyridine at 25 degrees Celsius. Pyridine reacts with HCl that then precipitates as pyridine hydrochloride, thereby making the reaction irreversible. So benzene and pyridine is another reaction, so that to make the reaction irreversible. The concentration time data is given in the table, was obtained in batch reactor. Here you have time and concentration data. At T equal to 0, Ca is equal to 0.05 molar. So if you look at here, T equal to 0, and then the title of the concentration is concentration times 10 power of 3. So basically, if you want to write it in unit of mole per decimeter cube, this is actually 50 times 10 power negative 3. That is 0.05. Okay, so this is 0.038. I would suggest if you want to try this exercise, write exactly the value here, 0.05, 0.038, 0.036. Okay, so that you are not going to neglect this time times power of 3. Okay, given here also the initial concentration of methanol is 0.5 mole per decimeter cube. Part 1. Determine the reaction order with respect to triphenyl methyl chloride. With respect to Ca only. Okay, not Cp, Ca only. Part 2. In a separate set of experiments, the reaction order with respect to methanol was found to be first order. So another set of experiment. Determine the specific reaction rate constant. That is the equation. Sorry, that is the question. Okay, this is the solution. Okay, first is step 1. So this is algorithm by fogler. Postulate a rate law. So initial guessing is negative RA is equal to KCA power alpha, CB power beta. Number 2, process your data in terms of measurable variable, which is in this case is CE. So that is a measurable data because that is data given in the table. The concentration of A with respect to time. Number 3, look for simplification. Okay, because concentration of methanol is 10 times the initial concentration of trimethyl trimethyl chloride, that is A. Concentration of B is 10 times the initial concentration of A. Its concentration is essentially constant. Are you agree? Okay. Whenever you have a very small amount of, in this case, species A, and a very big concentration or high concentration of species B, that is methanol, obviously we will say that nothing changed in terms of concentration of B, because it's 10 times bigger concentration than A, right? So what you can say here, CB is equivalent to CB naught. Initial concentration for the final, initial concentration for species B at the final, meaning the after duration, is similar to its initial concentration. Next is substituting for CB in equation E5 1.1. So you are going to substitute CB naught here. Okay, what you'll have there is negative RA initially is KCA alpha, CB beta. Since CB is equal to CB naught, you may have negative RA is equal to KCA alpha, CB naught beta. Further simplification is taking K prime is equal to KCB naught, okay, beta. Then you may further rearrange your rate law as negative RA equal to K prime CA alpha. Okay, now it looks like it is one reactant only. This is what I mentioned earlier. Differential methods also can be done for more than one reactants, but we need to have additional step. At the end, whatever value that you calculate from the graph, meaning the slope, and especially the intercept K, that is not a K, absolute K, that is the K prime, right? So the rest will follow the similar steps as we discussed earlier. Step number 4, apply the chemical reaction engineering algorithm, for which you have mole balance, then you have a rate law, okay. Then you have it, this one in terms of number of mole, then you may have it in terms of concentration as well. When you combine the mole balance and rate law, you'll have this. I hope you agree. Taking the natural logs of both sides, okay, then you may plot the graph. The slope of plot ln negative dCA over dt versus ln Ca will yield the reaction order alpha with respect to trimethyl chloride, that is species A. Step number 5, find negative dCA over T as a function of C. From concentration time data, we will find negative dCA over dt by each of the three methods just discussed, the graphical, finite difference, and polynomial methods. So let's start with graphical and numerical methods under differentiation methods. Okay, so this is the solution. I want you to spend some time to redo this example. It's not compulsory, but from my experience, if you just look at the solutions, you never know what is the difficulties that you are going to face. Alright, because there are several confusion or something that's you are going to stuck somewhere. Okay, so don't just look at the example, you need to try to do it. This is the technique. It's been explained in fogler. The derivative negative dc over dt is determined by calculating and plotting delta negative delta CA over delta T as a function of time. And then using the equal area differentiation technique. They have it in appendix to determine negative dc over dt as a function of CA. First, we calculate the ratio from the first two columns. The result is written in third column. Next, we use table E5-1.2 to plot the third column as a function of first column. Okay, using equal area differentiation, the value of negative dc over dt is read off the figure represented by the arrow. Then it is used to complete the fourth column of table E5-1.2. Okay. Once you have the histogram, whereby you already connect all the points, okay, this is the point you identify in the middle, or in the middle, connect the points. Okay, when you connect, the data of negative dc of dt is actually this intercept. Okay, this intercept. At 50, this is negative dc over dt. At 100, this is the value. At 150, the intercept. Between the line that you plot, this is the line that you plot. Okay, I put a purple. Okay. In this slide is the numerical methods. How to use the formula, just substitute. You may compare as well what is the value for negative dc over dt. Compare between numerical and graphical. So each of the value for the time, you'll have respective value of negative dc over dt. Okay, this is the summary of process data. If you compare differentiation methods using graphical, finite difference, and polynomial. Okay, as I mentioned earlier, you need to try. If not, it's really difficult to understand. So plotting this data on the graph paper, then the slope you get it as K prime. So your K prime is from the slope 0.1123 per mole per minute. Okay. Then you may recalculate your K, the actual K, because in part 2 you are given a statement that the reaction was said to be first order with respect to methanol. So beta is equal to 1. So basically, you are given the value of beta, assuming CB0 is constant, 0.5 mole per decimeter cube, and solving K yields 0.244. So the final answer, you must write the final answer. Negative RA is equal to K CA square CB power of 1. Okay, we know alpha, that is 2 from the slope. So this is integral methods, for which we'll explain it in the next video.